Okay, good day, everyone. Welcome to today's Mathematics and High Energy Physics seminar. We are happy to have Matilda Delgado, who will be presenting on Bordism and quantum gravity, as you can show on the screen. After completing her master's degree at the joint program at Ecoli Polytech and ETH, Matilda is on her PhD journey at IFT. Her research lies in quantum gravity, and one of the directions is a swampland program, and we are happy to learn her research today. And during the seminar, if you have any question, please use the raise hand button on Zoom, and I will grant you speaking permission. And we are grateful for everyone's participant. And now I will pass the conference to Matilda. Thank you for accepting the invitation.
Oh, thank you so much for having me. Hi, everybody. It's a pleasure to be here and to talk about Bordisms, which has been a bit of a passion thing recently, or at least what I've been working on mostly recently. So yeah, I just want to say, don't hesitate to ask questions. Again, there are no stupid questions. I'm going to try to write as slowly as I can, such that you can read what I'm writing, hopefully, and also so that you have time to think about what might be confusing or whatever question you may have. So let me get straight into it. The introduction and motivation. I see it's okay. It's changed. So the point is, right? Of course, at high energies, at the Planck scale, the structure of space-time itself starts to behave in a quantum matter. So what I mean by that is like subject to quantum tunneling and to superposition states. So that's, of course, when we need what? We need a theory of quantum gravity. It's a basic fact about our universe, right? It's just how things are. And throughout this talk, everything that I'm going to say should apply to any theory of quantum gravity. I'll of course be using string theory, being that it's our most controlled setup. It's a self-consistent theory of quantum gravity that has a very well-defined low energy limit that we can use to connect with the phenomenology in our world. So I'll be talking mostly about string theory, but it doesn't have to stop there. So if you won't need to know anything too serious about string theory to follow what I'm going to talk about. If you're interested in more details, I mean, there's a bunch of literature online. String theory has been around for quite some decades now, but you can also check out Max's seminar that he had in the same seminar series a few weeks ago. So that's a simple fact in nature. At this energy scale, the structure of space-time becomes completely almost unrecognizable. But at our energies, we have our energies being, of course, 10 to the 2 GeV instead of 10 to the 19 GeV. At our energies, we have an EFT, which has a cutoff lambda. So you can write an EFT just minimally coupled to gravity with some scalars that you'll generically have and whatever else you may want to put there. And so the point is, this EFT describes physics very well up until this cutoff. And once you get to this cutoff, so beyond it, we have new physics. Well, it's reasonable to expect that there's new physics just by the various problems that we have with the standard model. All of the BSM people, that they do, right? Figure out what kind of new physics we could have at higher energies. And so what we have to do at that point, in order to reach a new description, if you will, is integrate in all of the new states that might arise, which gives us what? It gives us an EFT, which I'm going to call EFT2, with some kind of cutoff lambda 2. Right? That's just the next step. And so you could imagine just continuing this process as you move up in energy. Every time you reach the cutoff, there's a cutoff because obviously physics isn't well described by EFT anymore, which means that there's some kind of new physics going on. You integrate that in, and so on and so forth, until you get something that looks like quantum gravity, which is up here beyond the Planck scale. But of course, in reality, we'll be mostly connecting with these kind of ultimate EFTs, the low energy effective actions of string theory of type 1, type 2A, type 2B, heterotics, and M theory that have cutoffs that can go all the way up to the Planck scale. So these are the theories that we're going to try to connect with when we start from low energies and start integrating stuff in. And so the right question to ask is whether or not we can do this with any EFT. Is this always possible to somehow keep integrating in new physics and arrive at something that looks like quantum gravity, or like one of the low energy effective actions of one of the string theories? And the point is that no, this is completely non-trivial, in fact. So for some EFTs, there is no way at all to obtain, an EFTN or whatever number of EFTs you have to go through before you get to the Planck scale that is compatible with quantum gravity. Equivalently, right, if we were to start with one of the low energy descriptions of string theory, that means that some EFTs cannot be obtained from one of these supergravity theories, or from quantum gravity, or its low energy EFT. That means there are some theories here that no matter how I compactify, I integrate out states from these original low energy effective field theories of quantum gravity, there's no way I can get this EFT here. Which if you think about is maybe perhaps surprising, but not that much, because there are so many different types of states that you could imagine integrating in without any motivation whatsoever. So that brings me to the point, right? This is the basic premise of the Swampland program. The fact that among all of the EFTs that you can have at R energies, all of these low energy theories that seem completely consistent from our perspective, there are only a few, or not a few, but there's a subset of these that you can actually relate to quantum gravity by integrating in all of these states successively. So the program of the Swampland is trying to identify this limit here between the theories that do belong to quantum gravity. So, if you will, these EFTs that can be completed to quantum gravity. So what we call the quantum gravity, oh, that's an ugly G. Quantum gravity landscape. And those theories here, that it turns out, although they look completely fine, again, from the infrared perspective, cannot be completed. So these are in the swampland, right? This is, of course, a playful term to contrast with a landscape. You would imagine like some kind of fields and trees, and the swampland full of crocodiles and junk. So the point of people that work on the swampland is to identify what differentiates between these two groups of EFTs. So under what criteria can an EFT actually be UV completed to quantum gravity at high energies? So of course, this was started in 2005 and has gained a lot of popularity since. There's a lot of different conjectures out there and a lot of different work. But so I'm not going to be exhaustive in any kind of way in these 2 hours. But if you're interested, of course, there's some reviews out there. I've picked this one out for you here by Van Beest, Calderoni Fatim, Fendersky, and Valenzuela. And of course, Irene herself, Irene Valenzuela, gave a seminar in the same series a couple of weeks ago. So you can also check that one out. Okay, so I think we're ready to go into the meat. So the question that you're probably asking yourself at this point is, how can we know what is good criteria for quantum gravity? Like, obviously, well, we all know that we don't have a full non-perturbative description of string theory or quantum gravity. Of course, otherwise we wouldn't be here. So what can we do in that case if we don't have this this at all? Well, we can look at examples from what we have control over in string theory. So which means it's low energy effective actions. So type 1, 2A, blah, blah, heterotics, and M theory can give us indications. And of course, we can look at the world sheets, which should have, you know, the same information. Well, it doesn't have this exactly, should have the same information as the low energy limits, but it's often that things are more obvious to see on the world sheet side of things, as opposed to the space-time side of things. So we can also look at the world sheets, which in some cases can even go beyond the low energy description. So that's for the string theory side of things. What we can also look at is black hole physics. You might know that black holes and the cosmological singularity are two places in the universe, well, types of places in the universe where we can actually see quantum gravitational effects. If you want the very fast, intuitive picture, it's like space-time is getting so small that it becomes, you know, Planckian size, and then you can't expect to be able to describe that thing without talking about quantum gravity. So for that reason, we apply a lot of what we know from black hole physics to the swampland in general, or at least a lot of our motivation comes from black hole physics. And relatedly, of course, we have ADS-CFT, which you can, okay, so it's holography, which you can build in string theory, but goes beyond that, of course. And if you think about it, black hole physics are also can also give us kind of holographic statements, you know, about how the horizon of the black hole contains all of the information about what's inside the black hole. That is a holographic statement, at least in the sense of the holographic principle. And I'll come back to this, but the holographic principle is really one of the biggest things we know about quantum gravity. That it should be, that's when gravity becomes holographic. But I'll come back to this in a little bit. First, I want to give you a couple examples, 2 examples that are going to be useful for the rest of this seminar of swampland constraints that we have, these swampland conjectures, so-called conjectures. The first is arguably one of our more studied and like on solid ground conjectures, which is the no global symmetries conjecture that says all global symmetries in quantum gravity have to be either broken or gauged, which means that, you know, you can start with an EFT at low energies that might have a global symmetry, but as you move up in energies, integrate in states, at some point you have to you have to break or gauge this global symmetry. So this was studied actually first, I think, by Banks and Seiberg a long time ago, 2006, I think. they first explored this idea, and various people worked on it throughout the years. So it's a very old idea, and I think most of the community agrees on this specific conjecture. So at this point, the first question you may want to ask yourself is, what is the global charge? So usually in physics, we talk about charges that you can measure, like, you know, that come from a gauge symmetry that you can measure with some kind of Gauss law, you know, integrating some flux through some compact space. The global charge is, for instance, it's like the B minus L symmetry in the standard model. So it's not something that you can measure from far away. You have to take your standard model Lagrangian, count all of the baryons and all of the leptons and get this charge. It's not maybe obvious just yet why this would be a problem with quantum gravity, but don't worry, coming to it right away. It's just so that you have some notion of what I mean by global symmetry. So of course, I'm going to go through one simple argument, a black hole argument. So it goes along this line of, well, the black hole physics side of arguing for small quantum conjectures. But Irene in her seminar discussed global symmetries in a lot of different ways. And so I encourage you to go check it out if you're interested. So again, no global symmetries. So now I want to give you the black hole arguments as to that might give you more of an idea as to why there should not be global symmetries in quantum gravity. Okay. So take any black hole. So, you know, you can shade, it has mass, it has charge, you can have, you know, angular momentum, like just consider, for instance, a massive black hole with no charges, no angular momentum, but you can play the same type of game with the others. And now you're going to throw any, okay, amount of global charge into this black hole. So you have, you know, this thing, which of course, this is more of an experiment that you would do in your mind than in reality. But if you were to imagine throwing in some global charge, by that, like, I don't know, some massless B minus L quanta somehow, then the point is that the radius, so the radius of the event horizon of the black hole is a function of the mass. It can be a function of the charge if the black hole had charges. And by charge, I mean charge is associated to a gauge symmetry, not a global charge. But so the point is that the size of this horizon is completely independent from the global charge that you threw into this black hole. Okay, so that means that for a black hole of some size, then there is an infinite number of possible microscopic configurations of the black hole. So of course, like you throw stuff into the black hole that's now inside the black hole. That's part of what we call the microscopic configuration of the black hole. So if you can throw any amount of global charge into it, and the horizon, the size of the horizon is completely unaffected, that means that this black hole can have, you know, infinite entropy. Because the entropy, I remind you, is the logarithm of the number of microstates of your black hole, the number of different microscopic configurations that you can build this black hole with. So the fact that this entropy is infinite, of course, is in huge conflict with Bekenstein's bound, which tells you that any region of space-time, any closed region of space-time, must have an entropy that is smaller than the area of that closed region over 4, which would be the entropy of a black hole, a physical black hole. But so the point is, if you were to allow for these global charges, then black holes themselves would violate Bekenstein's bound, which of course is problematic. I mean, this is again all of the black hole, how black hole physics and the holographic principle are constraining or are giving us motivation for our Swampland criteria. So this was to give you an idea of why global symmetries are problematic. But this, again, I said, is on a very solid ground. It's been proven in some cases. Well, first of all, in string perturbation theory. You can look in Polchinski's book. It's the basic statement that any global symmetry on the world sheet is gauged in space-time. That's the proof. Harlow and Ugari also proved it for some types of some specific symmetries using IDS-CFT. It's proven for non-invertible symmetries. I mean, like I said, this was just to give you a feel of how we argue for these swampland conjectures. But in some cases, like in this one, we're actually able to write down proofs, which is fantastic and should be the endpoint of any swampland conjecture. Okay, so if that's okay with you, I'll just move on to the next conjecture that I will use during this talk, which is the swampland distance conjecture by Ugari and Baffa back in 2006. And it says that in any EFT of quantum gravity, there is an infinite tower of states that becomes light at infinite field distances in field space. So it goes light exponentially with the distance in field space here. This is the mass of the tower, and in Planck masses, of course, Planck units. So what does this mean? It means that you have to, in these limits, what the theory is trying to make you do is to integrate in an infinite number of states, which of course is not well defined and leads to the breakdown of the EFT you're considering. So what you have to do in that case is change descriptions. So how do we argue? I'll give you some intuition as to what's going on here. How do we argue even for this swampland distance conjecture? Well, this is one of the cases, I mean, you can look at it from different angles, but this is one of the cases where there are a lot of examples in string theory that are pointing to this. And for instance, if you compactify your favorite low energy effective field theory of string theory, so your favorite supergravity, so again, type 1, 2A, 2B, the heterotics, on a circle of radius r. So compactify, what do I mean, right? These are supergravities that live in 10 dimensions. So by compactifying on a circle, I mean, you take one of those dimensions and you put it on the circle. And then you have to take all of the states that you had in 10 dimensions and decompose them, you know, the modes that propagate in the 9 remaining dimensions and the modes that propagate in the circle. This is going to give you a ton of KK modes on propagating in the circle. And the point is that at low energies, not the color font. At low energies, you get d-1 dimensional EFT with a Lagrangian that contains a kinetic term for a scalar here that can be directly linked to the size of your circle. Okay, this is what happens generically in string compactifications. You compactify on these weird, however complicated you want manifolds, and in the lower energy effective field theory, you have a bunch of dynamical scalars that are parameterizing the sizes and the structure of this compactification manifold. This is a circle. It's the simplest possible option. So you only have one parameter, which is the size, the radius. Okay. So then you have a 9-dimensional EFT, and you want to ask yourself, what happens if this field? So I took the field that is the logarithm of R because that's the canonically normalized option. Okay, so that the kinetic term is canonically normalized, and all of the infinite distance limits in field space that we discussed in the context of the swampland distance conjecture, we're only talking about scalars that are canonically normalized always. That's an important difference because if they're normalized differently, then they can behave in a whole lot of different ways. So what happens if our field goes to plus infinity? That means that our circle decompactifies. Okay, so that means that there's a tower of these KK modes that is becoming light. The KK modes have masses that go inversely with the size of the circle. So as the circle becomes huge, the KK modes become light, and we have to integrate them into our theory. A prime example of this, of course, might be any decompactification, but perhaps for the points I want to make today, the most interesting one is type 2A decompactifying to N theory when the dilaton goes to plus infinity. It turns out that the dilaton that you have in the type 2A 10-dimensional action is can parameterize the size of the extra dimension in M theory. Okay, so this is one of the maybe coolest examples of a decompactification limits where you're really completely changing the theory that you're considering. And in that case, the tower, you can think of it as a tower of KK modes. It's D0s and D0 bound states, but you don't need to worry about that for what I want to talk about today. So if instead you go to minus infinity, then the circle pinches off. It becomes a point. And so from string theory, okay, you have KK modes propagating, but you can also imagine winding the string around the circle. And this is going to have the opposite mass of the KK modes. Is going to go, not linearly, but well, basically they're going to become massless as this radius R becomes small. So the winding modes, well, it's a tower of winding modes, an infinite tower of winding modes. Okay, and the best example of this is for instance, T-dualities. I'll come back to these briefly in what comes, but the point of a T-duality, for instance, between type 2A and type 2B, is that you can exchange depending on if a circle becomes too small, then the best description is that of a T-dual theory, which has the inverse radius. So that's an example where the tower of states that seems to be coming down is the winding modes, but then the theory that you're going to change to is a theory which has a very well-defined space-time and is the T-dual theory. Yeah. So those are just was a simple example of what the swampland distance conjecture is about. And as I've tried to make clear, it is really a conjecture that speaks to the T-dualities in string theory. Not always, okay? You don't necessarily need to think of a decompactification as a proper dual theory, but since the dualities in string theory are often linked to fields going to plus or minus infinity to different infinite distances in field space, then it's very reminiscent of this, of losing control of the current TFT that you're using with a semi-classical spacetime and having to go to some kind of dual description that is better, where you have a new notion of semi-classical spacetime in a region that you wouldn't in the original theory. Okay, so the criterion for quantum gravity that I want to focus on today is that spacetime should be emergent in quantum gravity. Okay, what do I mean by this? I mean, of course, if you consider that the structure of spacetime is behaving in a quantum way, so subject to quantum tunneling and all of these superposition state, then there's no proper notion of like time and space on which to define your field theory or whatever you may have. So a true theory of quantum gravity, of course, should be background independent. It should not be constructed on a perturbation around some kind of flat space background like we usually do. But of course, the problem is that, well, I don't know. The tools at our disposal, so low energy EFTs of string theory. So again, the type 1, 2A, blah, 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 all the ones I've mentioned previously before. They're all supergravities. These theories are defined on backgrounds, right? So 10 or 11-dimensional flat space. So you're going to ask me, Matilda, what the heck? You told us that the most important, well, one of the most fundamental features of quantum gravity is that it's a theory where spacetime is emergent, that is background independent, and then you tell me that all the tools you're using are built on a background. So it's true. I mean, I can't argue with you, but the point is that you find this background independence in string dualities. If you think about it, the example that I was discussing before, it seems that when you take different limits in your theory, when when you're reaching the cutoff of your theory, right, when your theory doesn't become a good description anymore, you have to change descriptions to have a new low energy semi-classical spacetime. So let me give you a specific example. If you consider T-duality, so you take type 2A on a circle with radius R and a string coupling GS. String theory tells you that this is exactly the same as a different theory, type 2B, on a circle with radius 1 over R and a new string coupling that goes as the previous one divided by R in string units. Now, what does this mean? It means that when type 2A, of course, at weak coupling and low energies has a perfectly fine semi-classical description, which is given by type 2A supergravity. But as soon as you reach strong coupling or strong warping, then it can be better to switch to a dual description, where depending on the size that you choose for this radius, you can have a weak coupling, a weakly coupled theory with a perfectly semi-classical, perfectly low energy description of space-time. So the point is that the adequate low, well, semi-classical backgrounds that you're considering can change. That's how you find that's how, we argue that all of these supergravities are different facets of something way more fundamental, which is quantum gravity. And the fact that there's dualities between all of these theories tells you that the notion of space-time depends on the region of the theory that you're considering. It's something that's emergent. So for our purposes, it means that all backgrounds of perhaps compactified type 1, 2A, 2B, heterotic, and theory should all, well, I already said all, should be equivalent to each other. There shouldn't be a better option. That's background independence. So what I'm going to do today, in the rest of, this was the introductory part, in the rest of the seminar, I'm going to tell you how we can make this precise. We're going to do that with Bordisms and the Bordism conjecture. Okay. I haven't had any questions yet, so before I go into Bordisms and more of the mathy aspect of things, do you have any questions? Might be the right moment. Okay. Well, anyways, you can feel free to raise your hands and cut me off, whatever. Okay, so what are Bordisms? I'm going to give you a very brief crash course. So if you consider two different compactifications of string theory, or its low energy effective field theory again, on two different manifolds, MP and NP, of the same dimension. This is, it turns out, very relevant. We say that the two backgrounds are equivalent if there's a physical process that allows you to deform one background into the other, one compactification manifold into the other. And by physical process, I mean a finite action process. I mean a process that takes a finite amount of energy, otherwise it's not physical. So what happens is that you have this higher dimensional manifold, WP+1, I called it here, whose boundary are these two NP and NP. And this background, this higher dimensional manifold is telling you about, is describing for you a topology changing process that is allowed in quantum gravity. So that's that you can do in your quantum gravity theory. So in terms of math, we say that NP and NP are cobordant, which is exactly the same as saying they are bordant to each other. And I will use both terms during the seminar. I'll probably mix them up, but it means the same thing. So that's what we mean by two manifolds being cobordant. The point is that this gives you a precise notion of how different two backgrounds may be. So if they can be deformed into one another, we say that no, they're pretty much equivalent. You know, everything's fine. But if they can't be deformed into one another, then we have a problem, or then we have to look at things more closely. point is, all of these the point is identifying these topology changing processes that are allowed in quantum gravity. They are classified, or at least the equivalence classes are classified. Oh, don't worry, I'm going to explain what I mean. Are classified by this cobordism group of quantum gravity in p dimensions, so for p-dimensional manifolds. And this tells you about the equivalence classes under these so-called allowed processes. Now, what does this mean? It means that if two manifolds are in the same equivalence class, then they can be deformed into one another. If they're not in the same equivalence class, then they are very much disconnected. You can't deform one into the other. They are, they're not in the same equivalence class under these cobordism transitions. So you can make this precise, of course. I mean, I told you it's a math thing, and I'm being a real physicist here. But you can define a group structure under the disjoint union of two p-dimensional backgrounds. So if you take one manifold M1, they have the same dimensions, M2, then you can construct the Bordism of their disjoint union as follows. You have this sort of pants diagram, which gives you the equivalence class of the disjoint union of the two manifolds. Now, this, of course, is abelian because there's no notion of ordering in a disjoint union. And okay, I think, and then I can move on to the zero element, which is the so-called empty background. I'm going to be calling it nothing throughout this seminar. And so it's given by the equivalence class, the trivial equivalence class. So if you were to draw it, a cobordism to nothing would be taking your manifold M, and the fact that it belongs to the trivial equivalence class means that it's physically allowed for it to shrink into a point by a physical process. Now, this seems like kind of a drastic thing to happen to a manifold, but really you can have this happen without any energy. If you think of, for instance, Witten's bubble of nothing, if you're familiar with this, you have this compact circle that's shrinking to a point on the bubble wall, and this is a solution to Einstein gravity in the vacuum. There's no energy there. There's no physical problem with this. So that's what we call cobordism to nothing, and this is going to be something that I'm going to go into much more detail about in the rest of this talk. And finally, you have to define an inverse. So it's actually pretty simple. You just take the orientation reversed version of your manifold. So if you think of, if you just do a cobordism between M and itself, it's completely trivial. But if you want an inverse, then you have to sort of flip time like this and say that the disjoint union of M and its orientation reversed version is in the equivalence class of nothing. So that's how you define just the inverse. It's as simple as that. The cool thing, well, at least what I think is interesting, is when you look at what happens to the EFT that you've defined, that you obtained from these compactifications. So if you compactify whatever your favorite supergravity on this manifold MP, then you obtain an extended EFT in D minus P dimensions with a cutoff and everything. Fine. Then what happens to this EFT when your manifold is going through a cobordism to another manifold? Then on the one hand side, again, you just have your original EFT that you got from M, At the end of the transition, you have another EFT, because why not? You could just consider times that are way larger than whatever physical process made this transition, and you would just end up with the EFT that you would have normally gotten from NP. And then in the middle of the two, you have this sort of you have this sort of smudged domain wall between the two theories, where all of the degrees of freedom are, well, not all of them, but the ones that are relevant for the differences between the two manifolds are reshuffling and changing the EFT as you go through it. If you go one step further and consider the cobordism of a disjoint union, then you have the EFT for MP, and you have this completely disconnected, these theories are living in parallel universes, there's no contact between them, until a certain point where they join into the EFT that you would get with N. So in this sense, you have another sort of domain wall here, but it's this sort of 3-point domain wall where you could end up in one of the three theories. Just a pretty sci-fi. And so the start of the show, the cobordism to nothing, what happens then? Then you start with your regular compactification on MP. And then what happens when it becomes nothing? That means it's not that you didn't compactify your theory on anything here, right? It's literally that you compactified on the empty background. So there's just nothing here. There's nothing on this side. And from the perspective of the EFT, what you have is a boundary. You have a literal wall that if you were to go through it, you'd have nothing. Again, it's sort of like Witten's bubble of nothing. You can't define the metric beyond that point. Okay. Okay. So without further ado, I can go ahead and present the cobordism conjecture, which tells you that if you consider, the cobordism groups of quantum gravity, then all of the cobordism groups have to be trivial, no matter the dimension that you're considering. So what does that mean? It means that all p-dimensional backgrounds are in the same equivalence class that of nothing, in the equivalence class of nothing, okay? So in other words, it means all backgrounds can be deformed into each other since they're in the same equivalence class, and also into nothing. So this is really materializing the notion of background independence, if you think about it, because any two backgrounds are equivalent, and in fact, they can even disappear. They can even just become nothing. So this is how, if you will, the background independence of quantum gravity is materialized these cases where you start with a theory that has a background. Okay, this is the main intuition, I would say, around the cobordism conjecture. There are different ways to look at it, and I'll come to some of them in what comes next. But this is the one that I find the most compelling. Okay. So if there are no questions, I'll continue. So again, the fact that all cobordism groups in quantum gravity, no matter the dimension, should be trivial, means that all backgrounds in quantum gravity can be deformed into each other or bored into each other and to nothing. So from the space-time perspective, this means that any two d minus p dimensional EFTs of quantum gravity can be connected to each other with a domain wall. And this means, like, even between, I'm not talking about compactifications of the same theory. You could take type 2a and type 2b supergravity, and there should be a domain wall that connects the two. Do I know what it is? No, but I'll come to that later. So, and you know, they can be connected to each other with a domain wall, and that they should admit a boundary. So if you think about it, at least in one direction, the two concepts are not that far apart. Like if you consider, you know, a cobordism between two manifolds, then you have the effective field theories that are separated by some kind of domain wall. And if you were to consider the two cobordisms to nothings of two different manifolds, so the fact that all manifolds should be cobordant to nothing, then you have these two, like, kind of separated EFTs, each having a boundary. And if you were somehow to imagine gluing these two boundaries together, you know, as precise as the statement is not very precise, but there might be a way to make it precise, then, you know, you end up with the fact that there's a domain wall between any two theories. So at least in that sense, it's quite obvious that the two are the same. In the other, it's perhaps a bit less easy to see. Another thing that's interesting, and that comes back to what I was saying about quantum gravity being intrinsically holographic, is the fact that, you know, if all of these theories have a boundary, is this boundary the same kind of boundary as the ones that we talk about in holography? Are these boundaries, in a sense, a holographic screen that encodes all of the information about the bulk theory? So of course, that's a very interesting thing to think about. And in fact, Jacob McNamara wrote a lot about this in his thesis, so you should check it out. But it's kind of difficult to make this precise in general. But again, it speaks to the cobordism conjecture being about background independence, which and the emergence of space-time, and the holographic principle is in a lot of ways telling you about the emergence of space-time. You can't the theory on the boundary, which is non-gravitational, is encoding all of the information about what's in the space-time. So in that sense, there's a lot of ideas there that I think are really telling us something important about quantum gravity. Okay, so Now I'll tell you about another way you can think about the coordism conjecture, which is as a consequence of the no global symmetries conjecture. And I think this is the common way, or the most popular way to introduce the coordism conjecture. So it turns out that when the coordism classes are not all trivial, then you have this type of topological global charge. So let me write it out. Which is usually some kind of integral of some topological invariant, some characteristic class over the compact space. I'll give you examples, don't worry, I'm not going to leave you just with that. And this charge is coordism invariant. It's invariant under coordisms. So if that's the case, then that means that you can label, a background based on this charge. Which of course you shouldn't be able to do, background independence. You shouldn't be able to tell one background from the other. They're all equivalent to each other. So the statement that all the coordism classes are trivial means that the symmetry associated to this charge has to be, well, broken or gauged, like for global symmetries. I mean, it's exactly the statement of global symmetries. So by broken, what do I mean? I mean, there is an object in your theory that can absorb this charge. And by gauged, I mean that the compactification that you're considering on this manifold, this k-dimensional manifold, is inconsistent unless you add dynamical gauge fields to your theory. So in the case of this object that could break the symmetry, you can see it sort of this way, right? If you were to try to do a coordism to nothing with a manifold that is carrying this charge Q, like charge conservation, you can't just shrink it into nothing. The charge disappears. So if you were to have an object here that could absorb this charge at the point where it shrinks to nothing, then you're fine, because the process is physically allowed, okay? So this is the object. Okay. So before I go into how we define the coordism groups of quantum gravity, maybe is it time to, there's a question, great. Please go ahead.
No can speak.
Okay, thank you. So my question is, can you go to the previous slide?
Sure.
So by the global symmetry or the global charge, how about if the manifold you start with, the manifold itself has some space-time symmetry? It's also global symmetry.
You mean some kind of Lorentz invariance or
Yes,
something like that?
yes, like some, for instance, rotational symmetry.
Very good. So these symmetries in quantum gravity theories are gauged because of the graviton. These are gauge symmetries in supergravity. They're not global. In fact, any of these space-time symmetries. So the world sheet has the global symmetry that corresponds to the space-time symmetry, the Lorentz symmetry of 10-dimensional flat space, and it's a global symmetry on the world sheet. But in space-time, it's gauged by the graviton.
But in what sense you can distinguish this? Let's say the simplest, let's say U1 gauge symmetry. So why do the the electric charge is conserved? Because in some sense of the U1 gauge symmetry, there's U1 global symmetry hidden in it, right?
Sure, but the point of these global symmetries, if you recall from the introduction, are that you can't measure them from far away. There's nothing physical propagating them in space-time. So you can't do any kind of Gauss law for a global symmetry. It's like B minus L in the standard model. You have to have access to everything in your theory and just count them looking at the Lagrangian, but there's no type of,
right, but let's distinguish the symmetry at the Lagrangian level or the symmetry at the solution level. Okay, right?
Okay.
Let's think about a black hole. It's also a background, right?
Yeah.
So black hole has rotational symmetry, which can be measured at infinity, right?
Oh, you're talking about the angular momentum of a black hole.
For instance, yes.
Okay, so these
do you call that a global symmetry or gauge symmetry?
No. That's actually it's a gauge symmetry. You can measure it from far away, right?
Yes.
That's the difference I'm making, I suppose. There's a
so you mean from quantum gravity point of view, all this the no-hair theorem of all the black holes and the mass, the charge, angular momentum, I should view all these quantities as not as global symmetry.
Yeah, exactly. I mean, for the electric and magnetic charges, it's obvious because you have this, field strength and you can measure the flux through the horizon. So then it's obvious that this charge is coming from a gauge symmetry. For the angular momentum, I guess it's slightly less obvious, but
does it come back to my previous question? If you said they from some gauge symmetry, okay, no problem, I can accept that. But is it similar to the U1 gauge symmetry? I mean, I'm a little worried about if this quantity are associated with some global symmetry, which are hidden in some gauge symmetry. You know what I mean?
Perhaps things will be a bit clarified when I give examples of what I mean by global symmetries in quantum gravity.
Okay.
If that's okay, like that's I ask you afterwards if that made things clear.
Okay, sure. Yeah.
Okay.
Thank you.
Not at all. It is kind of a fine difference. I guess the way I think about it always is whether or not you can measure this thing from far away. If you can't, if there's no sense of measuring it from far away, then it's a global symmetry. Okay. So of course, how can we talk about the coercive groups of quantum gravity if it means somehow having access to all of the allowed topology changing processes in full-fledged quantum gravity? Of course, again, we don't have a full non-perturbative description of quantum gravity. Otherwise, we wouldn't be here. So what do? We make approximations. We turn off a lot of the fields. We just say that they're not propagating. We ignore singular spacetimes. We ignore non-geometric cases. So of course, these are huge approximations. But you'll find that even making these approximations, we arrive at some non-trivial predictions. So instead of considering the cobordism groups of quantum gravity, we consider the cobordism groups of some approximated notion of what quantum gravity is. So let me give you the first example. We observe that there are p4 mu1 gauge symmetries in quantum gravity. They're the Raman one in the type 2 strings, but they exist in general in any low energy effective field theory of quantum gravity. So then we can just consider this ingredient with all of the other ingredients turned off, and consider the cobordism groups of oriented k-dimensional manifolds with some p-form gauge field propagating through it. Okay, and then in order to get the equivalence classes, we have to mod out by cobordisms, by all of these processes that can allow you to deform one of these manifolds into another. So in general, there's not much to say about this, but for the specific case of p plus 1 equals k, then you can have some flux going through your compact sphere, or a sphere or a space. It doesn't need to be a sphere, of course. So this gives you a charge this charge that if you were to do a cobordism to nothing, you would be blocked by the fact that you can't shrink this charge into nothing. And it's a cobordism. The fact is that it's a cobordism invariant. If you take a cobordism from a manifold np plus 1 to a manifold np plus 1, so with some kind of high dimensional manifold here, then the charge that you're originally considering is q, and the final charge is, say, q prime. Then you can write down the integral of the exterior derivative of the field strength. And through Stokes' theorem, you know that you can come down to the boundaries of this higher dimensional manifold, which by construction is literally q minus q prime. And on the other hand, since fp plus 1 is already the exterior derivatives of this gauge field, then the Bianchi identity tells you that this is 0, and so that the two charges are equal, so that the two charges are cobordism invariants, such that you can label compactifications on p plus 1 dimensional manifolds by q. So this q is in the compact space. It's just, from the EFT's perspective, it's just this number. And yet it's telling you that somehow two backgrounds are not equivalent. You couldn't deform a background with charge q into a background with a different charge because of physics, because of how things are made. So that means, since these charges are taking values in the integers, sorry, then it means that the cobordism groups that you're considering, the group of some p-form U1 gauge field flowing through a p+1 dimensional manifold, closed oriented manifold, is Z, which is not the trivial, which is not nothing, right? So this is a problem. This cannot be. However, I mean, flux compactifications have been around for what, 20 years? They're perfectly consistent. There's no reason to think that this would be a problem. So then what can we do? We have to break the symmetry with an object. So what kind of object can absorb this charge so as to break the symmetry? Well, then in this case, the answer is quite obvious for those of you who are used to these types of constructions. It's magnetically charged d minus p minus 2 branes. These are literally the objects that source flux in the transverse sphere in the first place. So if you were to consider your compactification with the flux creating this charge, and you shrink to a point, well, if you place the appropriate d brane here, which is a d minus p minus 2 brane in this case, this object is going to be able to absorb all of the flux charge that you have in the manifold, and you'll be allowed to shrink the manifold to nothing without a problem. So in this way, the cobordism conjecture, this very simplest example that we always take for the cobordism conjecture, is that just by using the fact that there are p-form U1 gauge fields in your theory, then you know that there has to be the corresponding brane to source and absorb this thing. I don't know if that makes the picture a bit clearer. So this charge here is in the compact space. There's no, like in the EFT, you would have no way of measuring it. It would just be like this everywhere present charge Q. Does that clarify things a bit? Okay. Let me know if not. So that was the simplest example. The next one people usually do is okay, string theory has fermions. I mean, there's fermions at low energies, so somehow string theory, quantum gravity, again, I'm biased, has to have fermions, has to be compatible with fermions, which means that when you compactify, you have to compactify on manifolds that can have a spin structure, so on which you can define fermions. So that means in math that they have to be oriented and have a vanishing second Stiefel-Whitney class. But we don't need to go into the math details. So if you look at the Bordisms between manifolds that have a spin structure, you're looking at spin Bordism groups, which have been known in mathematics. I mean, I'm sure you've heard about them in other contexts than this one. So of course, here we're considering that all other fields are turned off. And I snatched this table of spin Bordism groups from the original paper by McNamara and Waffa, who are the ones that conjectured the Bordism conjecture back in 2019. And you see it right away that there are Bordism classes, Bordism groups that aren't trivial. For instance, there's this first one here. This first, so there's not even a compactification here. This is zero dimensional. So we're really talking about the the 10-dimensional supergravities or the 11-dimensional N theory, right? So the fact that zero spin is not zero, for instance, we could talk about the other ones, but this is the one I'm going to focus on. It means that there is, I mean, these supergravities, of course, are consistent. I mean, there's no reason to not think they're consistent or that this thing has to be gauged for some reason. So there has to be a codimension 1 object a boundary that kills this charge. So it's what people call a spin defect. So then that means that all of the supergravities we know and love have to admit a boundary beyond which there is nothing. So there are cases where it's quite obvious what this boundary is. Like for M theory, you can put M theory on an interval. That literally means that you can end it somehow at a point. And as we know, the boundaries on this interval are the place of the Hojava-Witten wall, which were studied back in the day, and have all of the right degrees of freedom so as to perfectly end N theory on each side. For type 2A, we can just take the Hojava-Witten wall, and put it on the M theory circle that gives you type 2A, which in type 2A language ends up being some O8s plus some D8s that you need to cancel the tadpole cancellation equation. So this is a type 1 prime theory, essentially, the fact again that you can put type 2A on an interval. But for what about type 2B theory and the heterotics? I mean, it's for some reason that we never talk about these theories necessarily on like some kind of interval. It's not clear at all what kind of boundary these theories may have. And in particular, they're chiral, right? If you think about a boundary, it kind of acts like a mirror. So if you have a non-chiral theory, then things are somewhat easy to define because the theory in the mirror and the theory outside of the mirror are the same. But when theories are chiral, then you have to find a way to properly end these chiral degrees of freedom, and it's not obvious at all how to do that. So this is a great open question. What boundaries these theories admit? We expect them to be highly non-supersymmetric, perhaps even like unstable, so that they only exist for the fraction in time that it takes when you're doing this process. Okay. So that's about as much into detail as I'm going to go about these ingredients that we can add in to the cobordism groups. So we started with the fact that string theory has p-form gauge fields, p-form U1 gauge fields, and we found that in order for the cobordism classes to be trivial, we need to add branes. So great, we post-predicted the existence of D branes. Then if you consider spin Bordism, we know that there has to be these defects, and for some cases we know them, for some cases we don't. It's exciting actually to predict these kind of boundaries, because then you could imagine gluing two boundaries together, and how, like if you knew the boundary of type 2b, you could maybe glue it to the boundary of type 2a and have a sort of transition between the two. But so the point of this cobordism story, if you say the big picture is that you want to keep adding in ingredients and get closer and closer to true notion of what are the cobordism groups of full-blown quantum gravity. The reason why it's hard to do this is because the math behind it is quite non-trivial, to say the least. Actually, so when you want to add structure to your cobordism group, this usually comes in the math language to come down to trivializing some extra characteristic class. And then you can compute the cobordism groups using the Atiyah, Hirzebruch, and the Adams spectral sequences. So these are based on generalized cohomology theories. So in a lot of ways, you can understand perhaps the physics of it, but the mathematical details are quite, well, they are something to handle that I would have a hard time telling you more about. But if you're interested, you can look at lectures, they're on YouTube, by Arun Debray, who went into the details of these spectral sequences. And now I'm going to move forward to a slightly tangential topic. So if you want to know more about pure cobordism conjecture lore and have more examples of how we gauge and break these symmetries, you can look at the lectures by Miguel Montero on YouTube as well. There's 3 of each. So that's more information that you can get from here. Of course, I had 2 hours, so that's all the detail I can go into for now. But so now I'm going to focus on something slightly different, which is, so far we've looked at the cobordism conjecture in this sort of kinematic sense that, oh, okay, we have to break these symmetries, so we have to have these objects. The manifolds you should be able to deform them into one another. But what does that mean? Like, if you have all of these domain walls between these different theories and you have these boundaries, then what do these things look like from the perspective of space-time when you actually solve the equations of motion? Okay, what would such an object back react on space-time like? So this is what we call dynamical cobordism. So you can think of it as cobordisms, but solving the equations of motion. So again, that means how do the defects, these objects that the cobordism conjecture predicts, back react on space-time? Like, what would a boundary of space-time look like? So this is really giving you the IR perspective on these objects. And you'll understand better what I mean by IR in just a few seconds. So we looked into this and asked ourselves a question: what happens when the compact space, here this p-dimensional manifold NP, shrinks to a point along some dimension of space-time? Like, solve the equations of motion and tell me what that looks like. So, well, actually, we did better than that. We searched through examples, existing examples in string theory. what we found is that they generically look like this. And what do I mean by look like this? I mean there are scaling, specific scaling relations. Where the Ricci curvature, okay, this is the curvature scalar, goes exponentially with some parameter times the distance in field space here. Similarly, the distance to this point goes like this. So let me explain what these things mean. First of all, why am I talking about fields in the first place? Well, as I mentioned previously, when we compactify in string theory, we end up in the lower dimensional effective field theory with a bunch of dynamical scalars that are parameterizing the sizes and the structure of the compactifying manifold. So these sometimes are the scalars that are going to be going to infinite distances in these limits. You can think of it actually, it's quite intuitive, because if you say that this is a size R and you're canonically, oh, I'm using R twice. So if this has a size L, then your canonically normalized scalar is going to go as a log of L, as I mentioned earlier in the talk. So as this manifold is shrinking to a point, this scalar is going to minus infinity. What that means is that the kinetic energy of the scalar in this very localized region of space-time is becoming huge. It's completely exploding. So if you think of it from just the simple perspective of GR, this is backreacting on space-time and creating a huge singularity. So that's why the curvature scalar is blowing up with the distance in field space. So here I should put absolute values, because it doesn't matter if it goes to plus or minus infinity, it's blowing up. And this is just to tell you that it is as we are getting close to this point. So it's a finite distance thing, okay, in space-time. So this, of course, is completely singular. From the perspective of the effective field theory. But the lore is that it is resolved in the UV with a finite tension object. What do I mean by that? I mean, the simple example of D-branes. D-branes from the supergravity perspective, if you look at the metric, there is a singularity there, right? Like, but nobody's worried about it, because we know that D-branes in full-blown string theory are perfectly fine objects on which the open strings end, but the supergravity description doesn't have access to everything. It can't tell you about the intrinsic nature of this D-brane. It doesn't tell you about all of the massive open string states that are ending on it. So that's in what sense, from the supergravity perspective, it's singular, but in the UV, we're not worried about it. So this is what should happen for any cobordism to nothing. In fact, for the D-brane case, I just wrote it down explicitly so that you can see that we're actually just using metrics and whatnot. I didn't write down the gauge fields because it's irrelevant for this. But so the D-branes have this metric, this solution in 10-dimensional type 2 supergravity, and this dependence on the dilaton. And so if you compactify on the transverse sphere to the D-brane, so this S8 minus P, then you get this lower dimensional P plus 2 dimensional effective field theory that has a dilaton, because there's always the dilaton, and then this scalar and a potential for the dilaton and the scalar. Now this potential exists because of the curvature in the sphere. This gives you a term in DIR, and the flux that is flowing through the sphere, this 8 minus p dimension form flux. So then if you look at how the curvature scalar is going near this d-brane, and if you look at how the distance in space-time scales, this distance to the d-brane scales with the field space distance, which in this case, d is akin to like 5 plus sigma, then you'll get exactly these things. Where this delta now, it's a parameter, and it's equal for the d-brane case specifically to this. So this is something that you always have to fit sort of to your solutions. So again, this is just exemplifying how you can realize these, the d-brane example that I described in cobordism. You can describe it dynamically, very precisely, as this sort of end of the world kind of solution, where everything's blowing up near the brain, and everything seems singular, but at the end of the day, it's just the normal back reaction of a DP brain. Nothing to worry about. Okay. Any questions about that part? Okay, so we have two perspectives on this, right? We have the cobordism conjecture, which is this kinematic statement, is very precise, mathematical, and you know, doesn't involve any kind of energy scales or whatever. It's predicts boundaries that can be or not dressed with defects. Like it predicts a boundary. If the cobordism classes all vanish in the first place, then these theories still have boundaries, but you don't have any kind of weird thing, weird object that has to absorb anything at the boundary. These weird things I'm talking about are these objects, these defects. On the other hand, dynamical cobordism just tells you about this IR perspective of things. So how can you solve Einstein's equations if the compact space is shrinking to a point? And turns out in dynamical cobordism, things are always singular. So in that way, it's kind of blind to any of the cool UV physics that you would expect from these objects. In fact, if you know there is a boundary, then generically you can show that it behaves as an end of the world kind of singularity in the IR. I say generically because there are cases like in M theory that have so much supersymmetry that there's no singularity at all. Like if you put M theory on an interval, the Harava-Witten-Wall story, there's no curvature blowing up near the boundary, right? It's completely smooth. Supergravity is completely blind to the fact that space-time is ending. And we attribute that to the fact that there's just this, the case is just super duper symmetric, right? But in general, when you go to lower energies, there's always this type of singular behavior, which is just, again, it's nothing to worry about. It's just a supergravity not being able to resolve this object, which you should expect. Then going to the other way, like say we devised an end of the world solution where the compact space is shrinking to a point. Can we really say that this object is describing the low energy, the back reaction of an actual UV defect? Can we actually say that? So that's the question, right? Well, when we have an end of the world singularity, how can we be sure it describes the back reaction of a UV defect? UV object predicted by the cobordism conjecture well, it turns out it's not that easy, right? Because, well, what should in this case, we were just considering the simple case of maybe some scalar fields and the compact space shrinking to a point. So you can make sure that the object has finite tension, which it absolutely should have if you're trying to make it an object of cobordism. Cobordism, again, are physical transitions. They're finite tension transitions. And when you have these singular things in the EFT, it's not always clear that you're able to achieve this. A lot of cases, if you were to actually write Dirac delta source for this object and solve things with the tension and perhaps some dependence on the dilaton, you'll see that the tension is actually infinite. So that means that whatever you found, it takes infinite tension to warp space that way, which tells you that the object you found is not an actual object. It doesn't make sense. So does it have finite tension? Does it source the dilaton? It could. Is it charged? Is it flat? If you think of the bubble of nothing, it's not flat, right? And yet it's tensionless and it's ending space-time. So there's a lot of variables there. Then you can check how does it behave under T-duality or dualities in general. Like if you know the boundary in some frame, you might be able to relate it through dualities to the frame you're currently in and see if the end of the world thing that you have is reflecting the right properties, okay? That's some intuition you can get from dualities. Okay. So one of the last points I want to make is that again that the swampland distance is relating the cobordisms to the swampland distance conjecture. Again, let me just tell you what the swampland distance conjecture is about, in case it's gotten lost in the 2 hours of me ranting about Bordisms. It tells you about the breakdown of the EFT, because you can't integrate in an infinite amount of states. It also tells you, it speaks to the fact that you need to change descriptions. Change duality frames, if you will, which in turn, remember, tells you about the emergent nature of space-time. What we found in these end of the world things, end of the world walls, this IR singularity that corresponds to this shrinking of the compact space to nothing, is that these end of the worlds are always probing infinite distances in field space. Be it the dilaton, be it the size of the compact space itself, somehow these, as you get close to this wall, this end of the world wall, you're going to infinite distance in field space, okay? So the connection is not perfect, but you can sort of see how the swampland distance conjecture on the one hand side and the cobordism conjecture can be sometimes related in this dynamical sense. Because if you try to implement the cobordisms to nothing that are predicted by the cobordism conjecture, solving the equations of motion, right, dynamically, then you end up often exploring these infinite distances in field space. So it becomes a natural question of, is there always an end of the world brain for probing any infinite distance in field space? So in this way, the dynamical perspective on things is sort of linking or creating at least a connection between the two things. And this again, so those of you who've seen the Irena's seminar know this, but the main points of, or one of the main objectives of the swamp plan program is to, in fact, reduce the number of conjectures that we have to a minimal set, which we think to be are representing, the true fundamental aspects of quantum gravity. So this is pointing to another connection between swamp plan conjectures that, from the outside look a bit, very different. Interconnectedness. Maybe there's too many ends there. Connected conjectures, or finding connections between conjectures is always a great thing, because it's telling you about the underlying fundamental nature, or principles of quantum gravity. So in this case, or at least what I've made this talk about, it's emergent space-time or background independence, perhaps. Okay, so then I'm ready for my conclusion slide. Just a giant drawing. So we have all of these swamp plan conjectures, right? We have no global symmetries. We have the fact that there are string dualities, or relatedly, the distance conjecture. And then, there's a bunch of other ones. And so these are meant to be the materialization of true principles of quantum gravity. In cases, of course, where you have a background, you're not really showing the true quantum nature of the gravity that you're looking at. So we focused on how specifically the background independence and the emergent nature of space-time appear in these low energy theories, which is through the statements that all backgrounds should have this vanishing of the cobordism, or trivializing of the cobordism classes. And we've seen furthermore that sort of the no global symmetries implies it for topological global charges, and that the dynamical aspect of how these transitions happen links it to dualities and to the distance conjecture. And yeah, I think that's everything I wanted to say. The cobordism conjecture is Bordisms in quantum gravity lets you put into very precise mathematical statements the fundamental fact about quantum gravity is that it should be background independent, and that space-time should be emergent. So that's all I have to say. Now, of course, you can ask me any number of questions you like.